Our next speaker is Dr. Guillem Anglada-Escude from Queen Mary, University of London, and the title is Proxima b and the search for terrestrial planets around the nearest red dwarfs.
You could see it, right? It's coming. Okay. It's just a test. Okay. So, now we are going to change logarithmically the scales where we are talking about, because we are going to talk about not galaxies anymore. We are going to talk about the really nearby universe, as close as it can be while it's still astronomy and not planetary sciences, which is looking at the nearest stars and looking at the planets around them. Here, it's kind of a summary of my talk. Basically, I'm going to tell you about a bit the work we did to finally detect, or what we think we have detected, a planet around Proxima b, which is the nearest star to the Sun, as you well should know. We had an outreach project and a lot of activities around it. This was done from La Silla with some other telescopes, and this is kind of the result, or what we think it's orbiting this very nearby star. This is the control room in La Silla, and these are the things that I'm going to show you. I'll start with a brief introduction, just again to put now our minds into the really local universe. Which is, let's look at the nearest stars, and this goes a bit slow, but it's fine. We can relax. I need water. Okay. So the image showing up here, we have the Sun here. We have Alpha Centauri there. It's a binary, and I'm going to just introduce briefly to put your mind also on how the local universe looks like in these very few slides. Also trying to show you that even though we are looking in the nearby universe, astronomical distances are huge, and we still need to keep that in mind, because people are asking, are we going to this planet? Are we going there anytime soon? So probably not, but it's usually useful to get a bit of an order of magnitude of things. Okay, nearest stars. Let's go. That's a solar system, and that's a pizza. But the good thing about this is that it gives you a very good idea of how large is the solar system. You put the solar system on the pizza, that would be the orbit of Neptune. Then you would have the orbit of Jupiter, would be the pepperoni slice in the center, and the Earth would be like a small ball of fat in that pepperoni slice. But then if you look at the nearby stars, let's see, we put our pizza here. So who can tell me where's the nearest star in this wonderful image of my home village? So the nearest star is in the container here, is in, I don't know, this tree here. There's a hill here. There are some forest here. Anybody can make a guess?
This hill.
Yes. So as you will see, oh, no, you'll see. So the nearest star is Alpha Centauri, and if this is about 20 centimeters, Alpha Centauri is at 3 kilometers. So from the edge of the solar system, or the solar system planets, to the nearest star, which is our nearest astronomical object beyond the solar system, there's nothing in between. So the universe is pretty empty. And yes, if we want to cross this gulf, if it took 30 years for the Voyager to reach more or less this distance here, so it would take tens of thousands of years to reach the nearest star. So yes, local universe, but still huge. So that gives us a bit of a sense of perspective. And no? Okay. No? Oh, okay, yes. Yeah, and that's just the introductory slide I gave you. So yes, just to give you the idea of what I call the Interstellar Golf. Okay, so nearest stars, that's the really nearest star system. It's a triple star system, Alpha Centauri. But the local universe, or the immediate neighborhood, is not only sun-like stars. Actually, this is kind of a diagram composed by the Recons group at Georgia State University, which kind of summarizes graphically what we have within about 30 light years, which is 10 parsecs. So basically we have stars like our sun here, Sol, a few more massive stars, and then we have this huge mass of, or not mass, but numbers of tiny objects which are cooler than the sun, orange K dwarfs, M dwarfs, and even brown dwarfs. So in a sense, when we study stars, and we don't care about the mass, but just the objects themselves, these stars are the dominating, the cool stars are the dominating factor in the stellar population of galaxies. Also, because we are interested to find things that are around stars, planets, for example, it's to expect that we will find, so if we find, for example, what we are looking for is potentially habitable planets or planets that might be hosting life or something like this. If we can find that these stars are hospitable to life, then probably means that the universe is full of habitable planets. If we find that the sun or even these massive stars have planets, this is a really small fraction in numbers. Okay, so just a quick summary. So this is the solar neighborhood in 3D. This is just a circle, 25 parsecs, really solar neighborhood. And just to put in context into the galactic scale, which is nice. I didn't know that the previous talk was about that. But we can see that we are this tiny, small circle here in the spiral arm of a galaxy. And then if you look at the galaxy, we are basically a pixel in this picture. And yeah, and imagine how small would be the pizza here. Okay, so we are in situation, nearby stars. Most of the nearby stars are red dwarfs. And we are interested in finding planets. So let's move to the topic, which is finding the planets. Okay. All right, so this is a picture. Time to drink. Okay, finding planets. Many of the people that is here, they are astronomers, so most of you might be familiar with this, but I understand that there are some geologists. So I'll just do a bit of an overview. Also, even if you're an astronomer, you don't need to know exactly what's the state of the field. So I'll try to give you an overview of where we are and why we are detecting these small planets these days. Okay, so finding planets is difficult because essentially we don't see the planets. Here I just want to illustrate how difficult it could be to get direct images of planets, for example. This is Tau Ceti, the nearest sun-like star that it's alone, because Alpha Centauri, for example, is a binary star, just an unremarkable star in the sky. This is the moon to scale. And let's try to see the planets here. So, okay, so that's Tau Ceti, a bit closer in. We don't see the planets. And here, you should see the pizza at some point. So let's see who sees it first. So now you see, that's the pizza. And the pizza basically is the orbit of Neptune. And this is when we go close in. So a couple points here I think that are important. So this is not as bad as it looks like when you look through the telescope, and you all know this. Because this is an image taken by a normal telescope. The image is badly saturated, and all the glare you see around here is not actually coming from the atmosphere, which is bad, but not as bad. What is coming, all this light here, scattered light, is coming from the lenses and the telescope surfaces. So it's not only that we need to improve our adaptive optics to, for example, get high contrast and see this star here at the center. If this telescope doesn't have extremely clean lenses and ways to deal with these imperfections at very small scale, all this scattered light goes into your image, and it's impossible to see the planet. So it's not just a matter of spending a lot of money building all these extremely expensive and high-tech devices, but we also need to keep the telescopes clean. That was the point. Okay. So it's difficult because we cannot detect the planets directly, so how we find the planets? There are 4 or 5 techniques that are used for finding planets. At least these 4, have produced results. Astrometry hasn't yet, but now there's a massive sky survey, as you may know. It's called the Gaia mission, and it's supposed to suddenly publish thousands of planets when the final data reduction is done in 2022. So it's already happening, and it's an important component. It will tell us something about the planets that the other techniques cannot. But I just want to focus on the 2 main detection methods, which are telling more about the populations, which is the transit method and the radial velocity method. The radial velocity method is what I work on, but I'll start with the transit, even though it's not the right historical order, because in a sense, it's kind of in the latest revolution in the field. However, the transit method doesn't work for nearby stars, as you will see in a second. Okay, transit, radial velocity, good. So transit photometry, you don't need to think about a lot. I showed this plot many times. Basically, a transit means we have a planet, we have a star, the orbit is aligned to our line of sight. So we see a dip when the planet goes in front of the star. This happens periodically, so you can see that this dip repeats and tells you the depth of the planet, the orbital period of the planet, and a few more information from here. The transiting planets are good also for a number of other reasons, because they can be characterized easily than the others, as you will see later. But that's basically the detection methods. We are talking here about detection so far, not characterization. It's different story. Okay, so here, again, mindset, we are trying to find planets around nearby stars, and I just want to discuss you a bit or show you why finding nearby planets around nearby stars with the transit method is difficult, just visually. So here we have the situation of the Kepler spacecraft, for example, looking at the star. We have a planet aligned to it. Okay, fine. But this only happens a small number of times, because the orbits can be aligned in any direction. So I didn't show you, but in this 30 parsec or 10 parsec sample that we have around 1,000 stars. So 1,000 stars, how many of these planets will actually be transiting 1,000 stars? And then you do the math, and you find out that only 2% would be transiting. So from 1,000 stars, you end up with about 60 objects that transit. So what Kepler did, instead of looking at these 1,000 stars, basically looked at very far away in a distant region of the Milky Way, a bit off the disk of the galaxy. So it observed 100,000 stars and found, or the prediction was that it would found about 2,000 planets. It actually found more, about 4,000 candidates, but this has to do with the fact that most of the planets show in multi-planet systems. So it's not that all stars have one planet. The idea now is that planets have one or more, stars have one or more detectable planet that we can characterize with Kepler or other tools. Okay, so all bit information that will be relevant later. Okay, all the stars have one or more planet. That's an important factor here. So here just, okay. To illustrate what I was saying with the Milky Way disk that we have seen before, we have the sun here. So Kepler looks very far away, so we have these many 100,000 stars. All right, so very quickly, this is a kind of summary plot of one of the, I think it's updated in July 2015, but more or less hasn't changed much at this point. So the Kepler space mission with the transit method has been able to detect many Earth-sized objects, even though it lost completeness when reaching orbital periods of around 100 days, and actually Kepler failed on its main mission, which was to detect Earth-like planets here. Apparently, this is because the stars are more active and more variable, so then you can confuse transits with other things. So it's a bit more difficult. And as you will see, it's massively more difficult to find planets on long periods because of the geometric component, but also because of the number of events you can register over a finite lifetime of a mission. Okay, very interesting. So Jupiter here, you don't see it here in the classic plot. There are here what we call the classic gas giants. And there are hot Jupiters here. Jupiter is very close to the star, very easy to detect. So this is why you have some of them. There are not that many. It's just an observational bias that we detect these kind of things here. But the good news on Kepler, and this was a bit unexpected, is this massive amount of super-Earths and Earth-sized planets. Super-Earth here, I just mean slightly larger than Earth, but smaller than Neptune. So that would be something here. And then all these planets here. And here, you're just losing detections because of the geometric probability of the transits. Okay, so this is where the transits have taken us. Now, we're interested in nearby stars. So in this case, radial velocities works a bit better. You are still a bit, you still lose a bit of sensitivity because of the inclination, as you will see. But it's much more robust. If there is a planet that you have the sensitivity to detect, you should detect it. In photometry, if you are only looking at 10 stars, even if your photometer is perfect, you can still miss the planets. Okay, so I guess that you all know that, but basically, again, we are not looking at the planets themselves. What we look is at the reflex motion of the star around the center of mass of the system. So you have the planet going around, and when the star moves around its orbit around the center of mass, you get Doppler shifted light. When the star comes to you, it gets blue shifted. When it goes away, it gets a bit red shifted. And you have all these spectral lines. This is what we monitor with our spectrographs at very high precision. Don't need to go into the details because this has been done by other people. Just remind you that the stellar spectrum has thousands of lines. We are not looking at just one. We are looking at, for a sun-like star, about 2,000 lines are being monitored simultaneously. This is an Echelle spectrum, a representation of an Echelle spectrum. Here, I think this is the sodium doublet, ultraviolet, blue, green. And green, by the way, is the color of the sun. So don't say that green is dark matter ever again. So you pick somewhere here. OK, so that's monitoring all these thousands of lines. This is how we get high precision. But for example, I don't have it here, but if you look at the spectrum of a cool dwarf, red dwarf, like Proxima Centauri, this is even worse or better for precision Doppler velocities. You would see the whole spectrum is covered in lines. So you don't even monitor line by line anymore. You basically take the whole spectrum and do not cross-correlation, and fitting forward modeling of the spectrum itself, and then you get a massive increase in precision. So even though M dwarfs are, these red dwarfs are fainter, we can actually achieve as much precision as for the bright stars as for sun-like stars. That was not well understood, let's say, before 2012. And this is one of the things that I did with my collaborators that kind of led to the detection of these very small planets around nearby M stars. OK, so that stopped working. Oh, it never worked, right? Doesn't matter. I never plugged it in. OK, so the Doppler method, very quickly. What we do, we look at the star, and we see how it moves. So if the star has a planet around it, you see the radial velocity of the star changing over time. And this is what you do, for example, in a year. You see this, you say, oh, the star is varying. Maybe it's a variable. Maybe it's a binary star. Who knows? It's just following a straight line. But then you wait a bit more. And at some point, with a lot of patience and a couple of years of telescope time, you see that start to fold. And now it changes. So here we have a pretty eccentric orbit, the detection of a planet with an amplitude of a couple hundred meters per second. That's a 5 Jupiter mass object around a half a solar mass star. A lot of data go into it. So just an overview of how the real data looks like when you have a detection. And it's not a perfect sinusoid because the orbit is eccentric. So at some times of the orbit, the planet moves faster. So you get this faster motion of the star as well. OK, so very quickly, the Doppler method, you may know that. Just a summary, an overview. So the first planet detected with this method is 51 Pec b, which was kind of the kickstart or the kickoff of the modern exoplanet era in 1995. The surprise was that this planet was found very close to the star with an orbital period of 4.2 days. So it's a massive planet, a massive gas giant close to the star. So this is when you have this massive amplitude of 50 meters per second. The star is moving like a car on this 4.2 day period. That was something not expected, and that had consequences on the first detections. For example, here, this is the number of planets detected by the Doppler method, the masses, as a function of the year. So 1995 here. So that's 51 Pec. And you see here, that's the American group that, for a number of reasons, were not proactive enough in reducing their data. Doesn't matter. So when 51 Pec was announced, they actually were able to reanalyze all their data in 3 months. And you have the 5 next planets reported within half a year. And then in 97, nothing happened because all the groups ran out of the useful data when they realized the planets could be at these short periods. They were not even looking at short periods for gas giants because the theory people would be saying, oh, these gas giants are very far away. If you find a planet that close, it will be a brown dwarf or something like this, and that's not interesting. OK, and the important point here is that what we call the Pale Red Dot campaign, which is the campaign that analyzed Proxima Centauri, basically reports this planet here, small one. It's about 1 Earth mass, and it's been detected in 2016, and you see it's kind of the lowest massed object. There's another important feature in this plot, which is that the precision started to improve, better instruments were built, but since here, nothing really happened from instrumental point of view. What happened here, we started to detect small things because people realized that we could actually start to look at M-dwarf stars, and in that case, we can get sensitivity to smaller planets. Another thing happened is that, for example, now from Kepler, we know that there are all these compact planetary systems. Planetary systems, many of them don't look like the solar system. You have this series of super-Earths very close to the star, which have a much larger Doppler signal, so the mass, we get smaller masses not because our instruments are better, now because we are looking more carefully on the stars. We have a well-educated guess when we put telescope proposals for this. Okay, so again, this slide, all these planets here, these are low mass and mostly have been detected around M dwarfs, which are these stars here. And I'm going to show you why and introduce you the final thing, which is the campaign. So planets around red dwarfs. Why we look at planets around red dwarfs, I have said this many times. Basically, red dwarfs are normal stars, but they are small and they are less massive, so about 10% of the mass of the sun, or 10% of the size of the sun. So you think, oh, it's only a factor of 10 improvement in sensitivity. No, that's not true, because, for example, the sensitivity in photometry scales as the square of the size. So you get a factor of 100 just because the transit is deeper. But also, when you look at small stars, your warm planets, the stars are less luminous, your warm planets are much closer in. So within a few months, you can recover many orbital cycles, so your signal also gets boosted because of that. That was not really acknowledged until recently, and that makes a huge impact on what you can do. So this is more or less where the pale red dot campaign was born, or based on all these arguments here. Why we call it pale red dot? I'll just do it fast. It's because there was the pale red dot picture of Carl Sagan of the Earth from the orbit of Saturn, and in a sense what we are looking at is this object around the nearest star that should inspire, it will be a dot or a sinusoid, as you will see, but should inspire scientific and excitement for space. That was a bit pretentious, I know, but we also wanted to do some outreach around it because the topic is intrinsically exciting. We didn't have to motivate the public. We just decided to use it instead of just promoting it. So, Pale Red Dot campaign, as you will see, it's not a lot of observations, and it means a change of paradigm of what we have to do to find these really small planets. Before 2012, when we actually started to go into business, there were around 300 measurements around Proxima by these two surveys. They didn't manage to find anything, but then it came my colleague, Mikko Tuomi, from University of Hertfordshire, who is an applied mathematician, and started to apply Bayesian techniques into searching for signals. And these Bayesian techniques allow you to make a global fit to the data, taking into account noise models, correlations, different instruments, to put them in a self-consistent way. And he found out that Proxima had 4 signals hidden in its data, coming from 2 different instruments that nobody had combined before. One signal has a period of 11 days, the other 35 days, the other 400 days, and the other 2,000 days. We are not sure what the signals were coming from. Maybe they were instrumental, who knows what. We tried to submit the paper. It didn't get accepted, fair enough, because this was really at the limit of what we understood about these M dwarfs, and Kepler was not even there. So we did not even know that these planets or these systems were common or not. So it was very early, I think. So we were not ready psychologically, including ourselves. So we got more data, we got some campaigns, look at Proxima and other stars, because we were looking at a few hundred stars that were published in different surveys. So we got more data on Proxima, 200 measurements almost. We didn't succeed in confirming which of these signals were real, but it was clear that at least one of them, the one that was at 11-day period, would show in our 10 long day campaigns. So here in gray, there's a stable star. Here in red is Proxima doing this beautiful apparent sinusoid. Yes. Okay. So we had the preferred period. We are not sure what was the real period still. So then we decided to do pale red dot, which is only getting 54 more measurements, but done in a different way, which is we don't get just tons of telescope time. We got only 20 minutes per night, so only 3 nights of telescope time were killed for this proposal. And then we sample the motion over 2 months in a row. So instead of just getting data all over the place, which makes very difficult to analyze the time domain, what we get is data continuously over 2 months, and then you see the sinusoid going up and down. The period is around 10 days, so we get it sampled 6 or 7 times, and that made a massive difference. Pale Red Dot was a huge campaign with a lot of people, and I'm not going to go into detail. All the co-authors are listed in the paper. but here, just wanted to show them. We used HARPS, but also 2 more observatories to photometrically monitor the star to be sure that the variability that we were seeing was not coming from the star, but was from a real planet. So we used HARPS. I don't need to show you because I'm a bit short. The Pale Red Dot campaign was a success. This happened early 2016. We only lost 5 nights or 6 by wet weather. We were really lucky because after us, it came El Niño and killed the whole season. But for us, it was good. We got almost 90% of the data was done. So that's what we wanted to do. 45 measurements at least. We got 56. So it was clear that it was a success, at least from the point of view of the science. Yeah, we did an outreach campaign with a website in partnership with ISO. They helped us a lot, and I can tell you more about this. We had the Twitter account, we had Facebook, we had discussions, we have articles from experts, even competitors gave their opinion on our blog. And this is the outreach team. And that's it, but doesn't matter. So this is the situation we had before we started the campaign. This is what we had after the campaign. This is a periodogram. If there is a peak, it tells you that there's a signal. And these are the thresholds, detection thresholds. You really want to be over the dotted line to claim a detection. So our campaign itself, because of the optimal sampling, already gave a detection the same that we would get with 500 observations before. And now when we combine the two, there's no, doesn't matter. Then you get a significant out of scale. So, I mean, the statistical significance is beyond doubt. The only tricky part is that, of course, you can always have fake signals coming from activity. So, however, we had this photometric follow-up, wonderful. We saw flares, we saw rotation of the star, but nothing that would resemble the same timescales of variability of the planet. So we were very happy. So from the signal, we get the properties of the planet, and that's it. And instead of showing everything that I wanted to show, I'll just skip to the last slide and tell you one thing here, that planets around nearby stars are very good because they allow us eventually to maybe do spectroscopy of the transits. And this is something I think Giovanna is around here, can tell you more about this. So we can detect molecules around these very nearby planets, especially if they transit. We don't know if Proxima is transiting. We have a Spitzer campaign within a month, so we'll know very sure. And the other thing is that extremely large telescopes have the potential to actually image this planet just because it's really, really nearby star. So maybe in 10 years, the instruments are already in place, are in construction. So it's just a matter of time until we figure out what is this planet about, if it's a telluric planet, it has an atmosphere or not. This is easy to say, but very difficult to do, but a lot of people is working on this. So I think that's it. Thank you.
So thank you very much indeed. We have only a very brief time for questions, so do we have any? Yes, at the back.
Arising from what you've been saying, of course, there is the related and wonderful idea of trying to send a microprobe, virtually a chip, to Proxima Centauri. But the worry that crosses my mind, and can you comment, is that the velocity that would have to be attained would be so great that even in the interstellar medium, it would encounter a considerable amount of resistance from the small number of isolated atoms floating about, and might even be destroyed in the attempt to get there as a result of friction.
Sure. But when Galileo looked at the moons 300 years ago, he didn't know what was in between, and now we have probes orbiting Jupiter, right? So it's not going to happen tomorrow, but at least it's a goal, it's a place, it's a target. So and it doesn't matter if we really reach there, but if we aim for the stars, then the solar system will be ours. So I think it's a wonderful thing, a motivational thing for the future generations, yes.
Okay, I'm afraid we have pressure of time, so I hope the speaker will stay for the reception afterwards and you can talk with him then.
Thank you.
So thank you very much indeed.